Welcome back. Today's goal of this lecture. Today I will see some interesting question as an exercise which is based on complex analysis. Actually this is based on topology. But at first I will tell you, in my previous video of complex analysis I had done one wrong. In my previous video I had seen the fundamental theorem for contour integral, which is if f is continuous on a domain f and capital F is an antiderivative of this function. In my previous video I had seen what is the antiderivative of small f. Then for any contour C in the domain D with initial point z0 and terminal point z1, integration along this contour say fz dz equal to capital F z1 minus capital F z0, where capital F is an antiderivative of the function f. Here I have done one wrong. In my previous video I had seen capital Fz equal to 1 over z, and in the region C equal to 2 e to the power I theta, where theta lies between minus pi to pi. In this region, since function has an antiderivative log z, and I had seen log z in complex analysis, this is the multivariate function. That means for one input there exists different outputs. So log z is a multivariable function. In my previous video I had seen this. So we cannot apply the contour integral, fundamental theorem of contour integral. So I had break this part. For breaking, here I have considered C1 from here to here and considered C2, where theta lies between pi over 2 to 3 pi over 2. Here C1 lies between minus pi over 2 to pi over 2. For this, here I have done the wrong. Integration along C1, here notice along C the value is at first the initial value, then minus terminal value. But here I have done in wrong. Here I have done log minus 2i minus log 2i. This is the wrong method. Here would be log 2i minus log 2i. This wrong thing I had done in my previous video. Similarly, when theta lies between pi over 2 to 3 pi over 2, then also would be this log plus 2 pi to minus 2 pi. Then the value would be I pi. I hope my all viewers have understood what I have done wrong. Okay. In my previous video I had seen simply connected and analytic that imply always independence of path. Also in my previous video I had seen antiderivative always imply independence of path. Today at first I will say some more exercise about this topic, then I will do some exercise which is actually based on topology. Now let's see another example. Consider the path integral integration z minus a to the power n dz. And here since integration z minus a to the power n, so the contour is a plus r e to the power it. And here I have considered this circle as a path, because this calculation would be more easier than other part where t lies between 0 to 2 pi. Then the integration 0 to 2 pi z minus a r e to the power I t to the power n, and dz means I r e to the power I t dt. So this value would be r to the power n plus 1 integration 0 to 2 pi e to the power I times e to the power I n plus 1 t dt. And notice for this function primitive would be 1 over n plus 1 e to the power I times n plus 1 t. This is be the primitive of this function. So after integration this value would be this. Now put the value, since along this curve, then this value would be just the value along the initial point and the terminal point. So this value would be from 0 to 2 pi. At first value, put the value at 2 pi, then 0, then put the value minus f of 0, because here f of t means this. At first consider f of this value would be at first f of 2 pi minus f of 0 times r to the power n minus 1, r to the power n plus 1. And when n equal to minus 1 and when n equal to n not equal to minus 1, because notice here value would be different when n equal to minus 1 and when n not equal to minus 1. When n not equal to minus 1, then when n not equal to 1, then this value would be 0, because here e to the power I times n plus 1 t, and we all of us know e to the power t is a periodic function. So when put the value 2 pi, then this value would be 1, and put the minus e to the power 0 means this value would be also 1, and 1 minus 1 is 0. So that means when n not equal to 1, then this value would be 0. But when n equal to minus 1, then when n equal to minus 1, then this value would be 1 over z minus a dz. I have considered gamma t equal to a plus r e to the power it. So z minus a would be 1 over z minus a would be 1 over r e to the power minus rt, and dz would be r e to the power it dt. Just cancel this part and cancel e to the power it to the minus it to the power it. Then this value would be here ir. This value would be I times 2 pi. So when n equal to minus 1, then this value would be 2 pi I. And this is very interesting. This is very interesting lemma. There exists a nice lemma. In complex analysis, let A be the interior point in the complex plane C, and r greater than 0, where gamma t equal to a plus r e to the power it, where t lies between 0 to 2 pi, and gamma lies from close interval 0 to pi to complex number, then for all n belongs to integer, integration z minus a to the power n dz equal to 0 if n not equal to minus 1, and 2 pi I when n equal to 1. Now I will see winding number or index of a curve. Suppose gamma k is a closed contour in the complex number C. And let A be given point in C omitted with gamma. Consider this circle, here A, here A plus R, and consider this circle oriented anti-clockwise. From here to here, this value would be pi over 2. But here I have considered the whole circle, that means gamma k lies from 0 to pi to complex number. I will say integration dz over z minus a. This value of the integration is 2 pi I k when a belongs to b z not r, and when a not belongs to b z not r, then this value would be 0. Here the closed curve, that means gamma a equal to gamma b and gamma kt equal to a plus r e to the power I kt. That means z equal to a plus r e to the power I kt. Then put the value here. Here dz means ir e to the power I kt. Now put the value. Z equal to a plus r e to the power I kt. So z minus a means integration 1 over r e to the power I kt, and dz means k I r e to the power I kt dt. Then just cancel this part. Then this value would be, and here the integration along the closed contour, so obviously integration would be from 0 to 2 pi, then this value would be 2 pi I times k. That means 1 over 2 pi I integration dz over z minus a. This value is any integer k. I hope my all viewers have understood this is okay. Over. This is the analytic definition of winding number or winding curve. If gamma encircle the point A k times in the counterclockwise direction, then 1 over 2 pi I dz over z minus a, this value is k. And if gamma encircle the point A k times in the clockwise direction, when this direction would be clockwise, means this direction would be clockwise direction. Here this is the anti-clockwise, where this direction would be such type direction. This means clockwise direction. Then the value of integer would be minus k. Then 1 over 2 pi I integration dz over z minus a, this value would be minus k. When gamma encircles the point A k times. That means let gamma be a closed contour in complex number C that avoid a point A belongs to C, then the index of gamma about the point A denoted as n gamma A. That means n gamma A equal to actually the winding number, and this value would be 1 over 2 pi I integration dz over z minus a. Let's see the picture. Here this contour around the point A closed anti-clockwise direction and B is outside this closed contour. So, in gamma A, this value would be 1 and in gamma B, this value would be 0. When this contour lies clockwise direction, then in gamma A would be -1, and since B is the outside of the circle, so in gamma B, this value would be 0. I hope my all viewers have understood what is the index or winding number of a curve. Okay. Next I will see some nice example. Actually this example, obviously this is useful for complex analysis, but actually this example from topology part. Now I will see S1. S1 means set of those element xy in R2 such that x square plus y square equal to 1. Now I will see is the set is open or closed. Here I will use the continuity property. We all of us know continuity property in topological space. F is continuous even only if F is continuous if and only if inverse image of every closed set is closed. Also F is continuous if and only if inverse image of every open set is open. Here I will use this criteria. S1. Here given S1. S1 means xy belongs to R2 such that x square plus y square equal to 1. Is the set is open or closed? Notice. We all of us know the set of continuous function is closed under multiplication or addition. Also, we all of us know the projection map always be continuous function because projection means xy goes to x. This is the P1 projection. Xy goes to y. This is the P2 projection. We all of us know this is be continuous. Because here the inverse image of open set, if we consider the open set AB here, then this inverse image would be this type of streak. Here 0A, here 0B. Similarly, here I have considered AB in y-axis. If I consider AB in x-axis, similarly the strip would be in the y coordinate, and this is the inverse image of open set always be open. Here A0 and here 0B. Well, all of us know this is the projection. Here notice projection is such type xy goes to x square and xy goes to y square. Then sum of two projection xy goes to x square plus y square. We all of us know this is be a continuous function. Sum of two projection is a continuous function. So obviously I have got this function is a continuous function. Now here the set is xy belongs to R2 such that x square plus y square equal to 1. And in R, obviously the subset 1 is a closed set. Why closed? Because for any x belongs to R omitted 1, we can find always B epsilon x belongs to R omitted with 1. And complement of the set 1 is always open. And since F is closed, and the function, the given function is product of projection, addition of the projection map, and this is obviously continuous. So inverse image of closed set is always closed. That means F inverse 1, and notice F inverse 1 means xy belongs to R2 such that f of xy equal to 1. Notice F inverse 1 means xy belongs to R2 such that f of x comma y belongs to 1. And this is actually S1. And that means, notice here I have used just the property of the continuity. Since the function is continuous, that means inverse image of closed set is closed. So S1 is closed. I hope my all viewers have understood this is okay? Oh well. Sn is a closed set because Sn equal to x1, x2, xn belongs to Rn plus 1 such that x1 square plus x2 square plus xn square equal to 1. Is Sn is closed or open? Notice here the function f from Rn plus 1 to R. And here f of x1, x2 up to xn equal to x1 square plus x2 square up to xn square. And since 1 is a closed set, so F inverse 1 is closed, and F inverse 1 is nothing but this set, similar to before. So Sn also closed set. Okay. Next, now I will see GLNR, where GLNR equal to A belongs to MNR such that determinant of A not equal to 0. And SLNR, we all of us know SLNR means A belongs to MNR such that determinant of A equal to 1. Now I will say GLNR is open set and SLNR is closed set. Here also I will use the continuity. First define the mapping. Here the mapping defined from determined from MNR to R such that the matrix x11, x12, x21, x22 equal to x11, x22 minus x12, x21. This is the determinant. And determinant is, since this is the polynomial whose coefficient is a matrix coefficient, so determinant map is always continuous because this is the polynomial function. Since this is the continuous, so at first I will say for GLNR, GLNR means determinant of A not equal to 0, that means determinant of R minus singleton set 0, and as R minus singleton set 0 is an open set. So GLNR is actually F inverse R minus singleton set 0. Therefore, since R minus singleton set 0 is an open set, so that implies that inverse image also be open set, because this is the definition of continuity. Inverse image of open set is open, and inverse image of R minus singleton set 0 is actually the GLNR. So GLNR is open set. I hope my all viewers have understood why continuity is useful. Next I will see why SLNR is closed set. Similar to before, SLNR means determinant of A equal to 1. Set of those matrices whose determinant is 1, and this is closed because SLNR is actually determinant inverse of 1. So I have seen few minutes ago 1 is closed set in R, because here matrix define determinant from Mn R to R. Since 1 is closed set in R, so it inverse is actually SLNR is closed in MNR. I hope my all viewers have understood. Similarly, next I will see set of orthogonal matrix is a closed set. Similar to before, because here orthogonal matrix means A transpose A equal to identity, and A transpose A means x11 square. This type of matrix x11 square plus x21 square, x11 x12 plus x21 x22. Here the entries is x12 x11 plus x22 x11. Here x11 square plus x22 square. Notice here is entry be a polynomial. So f is a continuous function, and ONR means F inverse identity. F inverse identity actually the orthogonal matrix ONR. And we all of us know identity means 1, and 1 is a closed set in R. So ONR is closed in MNR. I hope my all viewers have understood. This type of example and this type of question actually very important for higher study. Okay, I will stop here. In my next video I will discuss this type of question, some basic question, basic knowledge about complex analysis and topology, because complex analysis and topology actually same part. To understand in complex analysis better way, topology is more necessary. Okay, see you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.